Learning is the only thing the mind never exhausts, never fears, and never regrets. Happy evening to one and all present here. Extend my heartfelt welcome to Dr. Abba Khandelwal, founder AACST Nagpur and workshop mentor, and today's resource person for the session 5. Dr. Chitra Ravi, AACST Bangalore Unit Event Coordinator and Workshop Convener. Session Chairperson Dr. Ashish P. Sasankar, Principal Indraprastha New Arts, Commerce, Science College, Varda, and also the life member of AACST. I also welcome Dr. Dilip Kumar Bisoi, life member of AACST to this session. I welcome all the participants for today's online national level online workshop on quantum computing technologies exploring interdisciplinary frontiers organized by Association of all the computer science teachers. I welcome you all. I take this opportunity to introduce session chairperson Dr. Ashish B. Sasankar, Principal, Indraprastha New Arts, Commerce and Science College, Varda, and life member of ACST. Dr. Ashish B. Sasankar is a highly accomplished academic and IT professional with over 25 years of experience. He holds an MCA, MTech, MPhil, and PhD in computer science from RTM Nagpur University, India. Currently, he serves as a principal of the prestigious Indraprastha New Arts, Commerce, Science College in Varda, India. Dr. Ashish is also a PhD guide for computer science in the Faculty of Science at RTM Nagpur University, where he mentors numerous research scholars. He has an impressive record of 92 publications in national and international journals, from 4 patents and 4 books. He is a life member of AACST, IEEE, CSI, and the president of ICTRD. He has completed over 40 international and national certification in the IT field. So with this introduction, I welcome you, sir. And I now request Dr. Ashish B. Sasankar, sir, to declare the session open. Over to you, sir.
Thank you, ma'am. Thank you very much. Good evening to all delegates, esteemed colleagues, and distinguished guests. And expert for today's session, Dr. Abba Khandelwal, madam, who is the founder and are also guide. I'm honored to be a chairperson for the today's session. It's my great pleasure to welcome you all for the today's session on cybersecurity in quantum age. As we stand a cup of technology revolution, the fusion of quantum computing and cybersecurity presents both unprecedented opportunity and profound challenges. The quantum age promises to transform industry, enhance computational capability, and solve problems that are currently beyond our reach. However, with this advancement comes the potential to upend the very foundation of our cybersecurity framework. Our task today is to explore these emerging dynamics, anticipate the risk, and strategize how we can safeguard our digital world in this new area. I expect that today's session should be a very interactive, very interesting. As we have the expertise available, I hope that this session should be fruitful for all of you. Thank you, ma'am. Thank you. Thank you very much.
Thank you, sir. Now it's time to introduce our resource person. I take this opportunity to introduce our session resource person, Dr. Abba Khandelwal, ma'am. Dr. Abba Khandelwal, an esteemed and widely respected educator. She is the retired head of the Department of Computer Science at Hislop College, Nagpur. With an illustrious career spanning over 27 years as the visionary founder of the AACST, she has been instrumental in promoting digital literacy and advancing awareness of cutting-edge technologies. She holds dual PhD degrees in computer science and business management, showcasing her expertise in various areas. Her extensive involvement in academia includes over 2 decades of service as a member of the BOS in computer science at RTM Nagpur University, Nagpur. She has also worked in various capacities within university committees, contributing significantly to the academic community. She is celebrated as the cornerstone of computer science education at RTM Nagpur University. Dr. Khandelwal has authored several articles, acclaimed a book, and published 38 influential journal articles. She has been invited to speak at numerous prestigious institutions and events. We are honored to have Dr. Abba Khandelwal, a unique and visionary leader, as the resource person today. I welcome you, ma'am, and I request you to take over the session.
Thank you, Shruti. Let me share my presentation. So today is fifth session. Welcome one and all. Thanks from the heart, convener Madam Dr. Chitra Ravi, for transforming my dream into reality. Being the convener of this esteemed workshop, where all of us got a chance to upgrade our knowledge in the cutting-edge technology of quantum computing and share our knowledge too. Sincere appreciation to all the participants. Today, let us embark on a journey into captivating universe of cybersecurity, where the laws of physics safeguard our digital secrets. So let's begin. First of all, let's understand what cybersecurity is. It is a practice of safeguarding systems, networks, and programs from digital attacks. Isn't it crucial to prevent our data from data breaches and identity theft? Because otherwise they can undermine trust in our digital systems. So by protecting sensitive information from unauthorized access, cybersecurity ensures the privacy and integrity of data. In the era where quantum computing is on the horizon, these protections becomes even more crucial and critical, as quantum technology presents both new challenges and opportunities for securing our digital world. Now, let us look at some of the common types of cyber attacks to better understand the threats we face. So the first, there is hacking, which involves unauthorized access of data, often targeting the sensitive information or system. You must have heard many a times the system has been hacked. Then next we have phishing. Phishing, where attackers use methods like deceptive emails or messages to trick individuals into revealing their sensitive information, such as passwords or financial details. So if password is disclosed, then nothing is left in your hand. Another significant threat is malware, which is a malicious software. It is designed to disrupt, damage, or gain unauthorized access to the system. And finally, there is ransomware. A particularly alarming form of a malware is that it locks the users out of the system or files, demanding a ransom payment to restore access. Each of these attacks highlights the need for robust cybersecurity measures to protect our digital assets and personal information. That how the cybersecurity, then classical cryptography and quantum cryptography, they are interconnected, as they all play a vital role in protecting information. So classical cryptography is the traditional method. It is used to secure data through mathematical techniques, and this involves encryption algorithms that transform plain text into coded text, ensuring that only authorized parties can decrypt it. Example of these algorithms includes AES and RSA, the Advanced Encryption Standard, and Rivest-Shamir-Adleman. Then the process relies heavily on keys, secret values used to encrypt and decrypt information, and the security of classical cryptography is based on keeping these keys safe. So in cybersecurity, classical cryptography is fundamental. It secures communication, data storage, transactions over network. For instance, when we go for online purchase, the classical cryptography ensures that your credit card details or debit card details are encrypted, and thus processing them protecting them from unauthorized access. So as we advance into the quantum age, understanding classical cryptography remains essential, but we will also need to explore how quantum cryptography can enhance or transform these methods. Now let's look into the modern approach that enhances our data security by leveraging the principles of quantum mechanics. Let's start with quantum key distribution. This technique is the heart of quantum cryptography. Essentially, it uses quantum states to share encryption key securely. And if any other person other than the authorized one tries to intercept the key or hack the key, the act of trying to measure will be noticed immediately. And this is because measuring these quantum states actually changes them. And this makes quantum key distribution very secure against eavesdropping. We will look into this in detail later on as the session will progress. And as quantum computers are becoming more powerful, they could potentially break existing encryption methods, and quantum cryptography steps into the to address these situations. Who introduced quantum cryptography? In 1968, very few knew this, that Stephen Wissner from Columbia University in New York was the first to propose the concept. His seminal paper titled Conjugate Coding was rejected by IEEE, Information Theory Society, but was eventually published in 1983 in Cybe News. And a few notable researchers in quantum physics and computer science developed the concept of quantum cryptography. And one of the key pioneers in quantum cryptography is Charles Bennett, who along with Gil Brazard introduced the concept of quantum key distribution in their groundbreaking paper titled Quantum Cryptography, Public Key Distribution and Coin Tossing in 1984. Then let's look at the evaluation of quantum cryptography. The quantum cryptography began taking shape in 1980s, marked by the groundbreaking work of BB84 protocol. And this innovative approach emerged from the pioneering work of Charles Bennett and Gil Brazard in 1984. What they did, they demonstrated that photons can be used to transmit information securely. Once they guessed this from the quantum physics, then they started thinking about the secure transmission of keys. So the BB84 protocol, it introduced a method for secure communication by harnessing the unique properties of quantum mechanics. BB84, so this protocol is named by because both of them, the name starts with Bennett and Brazard. So from there they have taken BB, and it was successfully implemented in the year 1984. So the BB84 protocol brings the revolution. Now, what is BB84 protocol? It uses photons to transmit data over fiber optic wires. First of all, let us see what is a photon. The photon is nothing but a single photon represents a very tiny amount of light. A very tiny amount of light. So how a single photon can be generated might be a question in many of your mind. So you can drive a single atom by a laser and excite that. Switch off the laser. Now the single atom, after some fraction of time, depending of course on the atomic lifetime, it will emit a single photon. And nowadays a quantum dot is also on demand. So this is how the single photon, this is what a single photon is. And now let us look at what is polarization. Now the polarization the direction of electric field oscillations is what we call as photons polarization. So photons, which are particles of light, and they can have different polarization depending on how their electric fields are oriented. For example, the electric field can vibrate in horizontal direction, vertical direction, or at any other direction. It can, so in any of the direction it can vibrate, or any of the angle in between. The very fact that these photons can be oriented or they can be polarized in a specific direction. So this way the qubit can be implemented. So the qubit can be implemented using a polarization of a photon. So this is how the theory progressed. And then we need some, for polarizing a proton, you need polarization filter. It is also known as polarizer. It is an optical device that selectively allows the transmission of light with a specific polarized orientation or state while blocking all other light waves. So with different orientations, whatever light waves are there, they will be blocked, and only it will pass on or transmit the light waves with a specific which are specifically oriented in one particular direction. So these photons are polarized with respective polarization filters. So you can see in this diagram, this is your polarization filter. Now each photon represents a qubit, okay? And qubit, the quantum bit must have two distinct states, because bit means you are, everyone is very much familiar with the digit, our classical word digital, so 0 and 1. So even in quantum computing, we need 0 and 1. Our machine can still understand the language of 0 and 1. But these two distinct states which we will get a photon, so one will represent 0 and another will represent 1. So this is how we are going to use the photon, by polarizing it and using its states to represent 0 and 1. The polarization state of a single photon makes it possible. For example, horizontal and anti-diagonal polarized states are ascribed a logical value 0. So just look here. Sorry. These are polarized. This is for HV polarizer. So this polarizer will polarize the photon in either horizontal or vertical. So if it is polarized in horizontal direction, then the eigenvalue 0 is assigned to it, and if in vertical, next to it, yes, if in vertical, then it will be assigned 1. And then with diagonal is plus 45 and minus 45. So if it is on plus side, then it is assigned eigenvalue 1, or otherwise it is assigned 0. Now, I would like to explain you this once again, because this is a very important concept. So there are two types of polarization. One is linear, another is elliptical. We don't have to look after elliptical right now, because we are going to use linear polarizations. It has two states, rectilinear and diagonal. Now rectilinear polarization again has two types. One is horizontal and another is vertical. So many a times it is called as HV, or the HV. And then if diagonal polarization is also of the kind, so few researchers call this as DA, and many call it as only D. So even if I am calling a word D, it is DA. And if it is HV, then HV, we always call it as HV. It is pretty easy to see that we have two level systems in photon polarization, right? One is 0, another is 1. Now look at this. I have not written 0 and 1 like we used to write in our classical world. There we just simply write 0 and 1, but here I've written cat 0 and cat 1. So when you write a qubit, then this is the notation which you are supposed to use. The two states of rectilinear polarization, horizontal and vertical, they will be represented as H and V. And the two states of diagonal polarization, that is diagonal and anti-diagonal, they will be described as D and A. So consider H and V as 0 and 1 on z-axis and D and A as positive and negative along the x-axis. So you can see in this. Okay. Now, after this, the BB84 protocol model, it uses 4 polarization states. You can see in previous slide, it uses 4 polarization states, or you can see here, which are they? The horizontal, vertical, horizontal, 45 degrees right, 45 degrees left. The horizontal and vertical orientations are linear polarization, and so are diagonal. In 1992, Charles Bennett presented a new quantum key distribution protocol, which I have already explained you by his surname. And then the year after, actually, in 92, by his surname, and the year that was published, that is B92. But this protocol is essentially a variant of BB84, with the main difference being that B92 uses 2 states of polarization instead of 4 that are being used in BB84. And B92 is a 2 quantum state protocol, and with this architecture, an eavesdropper can also be detected. So polarized photons are transmitted to receiver over the fiber optical cables. So B92, don't get confused. Just I wanted to tell you that it is not compulsory that every protocol is going to use 4 polarized states. So BB84 has used 4, and we are going to discuss the popular one, the well-established one, that is our BB84. Now, in this picture, which you can see here, the polarized photons are transmitted to the receivers. How? Now, this is your polarizer. This is your polarizer. And in this polarizer, you can see there are 4 polarized states. One is this, another is this, third one is this, and 4th is this. And they are represented by different colors. Then I'll explain you in detail about this also. But right now, I wanted to tell you that how the polarized photons will get transmitted from sender to receiver. So sender is here, and to receiver, this is fiber optical cable. So they will go by one, and here at the receiver's end, they will be received. Now how? So at the receiving end, this is the picture of receiving end. So at the receiving end, there are 2 beam splitters. You can see here, this is a beam splitter for which one? HV, and this brown is for diagonal. So this is for, this will split the beams which are coming with bases HV, and then the horizontal or the vertical will be detected by the photon detector. And here, this is our diagonal splitter, beam splitter. So for diagonal bases, it will transmit them into the 45 degrees is diagonal. So again 0 and 1, then the photon detector will detect it. So photon detector, actually at the receiving end, 2 beam splitters, they create a quantum superposition. 0 and 1, they are placed in superposition, and then the photon detector will measure it mapping their states. So whichever will reach to the detector, to a corresponding bit value of either 0 or 1. So before collapsing, photon is in superposition state, and hence the result is still uncertain till it collapses. So when we measure the photon, it can only be measured when it collapses. So in superposition state, it cannot be measured. In superposition state, it may be 0 and or it may be 1, because you have already been explained everything about this, that what is superposition. So either it will be 0 or it will be 1, or any of the superposition state. It can remain in any of the superposition state. So here, till it is in superposition state, we are not at all sure rather in which state it is, but which value it has acquired. But when you measure it, then how it has been collapsed, that is the measurement will give you the value. So the result will remain uncertain till then. Now, this is the main why I was telling you all everything, because this is the quantum cryptography. I am going to explain you the complete picture, because now you will be able to understand that how will it proceed. So BB84 protocol proposed in 84 by Bennett and Brazard. That's where the name comes from. And the idea is to encode every bit of the secret key into the polarization state of a single photon. I hope you are getting me, that we will encode every bit of the secret key, because we are talking about the security, cyber security. So we are going to develop a secret key, and that secret key we will implement also in one-time pad. So how this will be implemented, how this will be utilized, that also I am going to explain you. But right now you have to understand that how the secret key will be generated. So now secret key, we are saying that using photons, it has been done. So every bit of that secret key, now in this picture, they have generated a secret key by passing 14 photons. So each of them is in one particular state. Now every bit, so say 14 out of 14 bits, we are the polarization state, we will place them in polarization state of a single photon. So first of all, we will have to have a photon source, and you can see this is the photon source. Now from this photon source, the single photons are being emitted, and they are passing through this polarizer. So each of the photon will get polarized. Now what will happen, that Alice will send a sequence of pulses. So here is Alice. Now, one thing I forgot to tell you, that very beautifully in quantum cryptography, they got rid of sender and receiver. And really, I like this idea of theirs, that they called Alice as a sender and Bob as a receiver. Alice is sender, Bob is receiver. So learning also becomes very fancy and interesting when we say Alice is sending the message, Bob is receiving it. So now what Alice, when I say Alice, it means that it is sender, and when I say Bob, that means it is the receiver. Now Alice has to send the photons. Now Alice encodes zeros in H polarized photons. So 3, while she encodes a V polarized photons, that are 4 here. So can you see that this horizontal and vertical, in this horizontal and vertical picture, the vertical one is in brown color and the horizontal one is in blue color. So they are brown and blue. So she has polarized 3 in horizontal, that means 3 this, and how many? She has polarized Y, she has polarized the vertical V, 4V. So 3H and 4V. Okay, let's see. This is 1. This is 2. and this is hiding here, this is third. Okay, so these are horizontal. Let's count the vertical. 1, 2, 3, and 4. Okay, so I think you got the meaning that what Alice did. She has encoded zeros into H polarized photons. They are 3. H में 0 है, and vertical is 1. So with vertical, you just put a finger upward direction and say that yes, remember vertical is 1, eigenvalue 1. So V, that is 4. Okay. But this happens only with the half of the cases because she has to polarize 14. We have already seen that in this example, they have taken 14. So out of 14, they have polarized only 7. Now, other half bits, G will polarize in using diagonal polarizer. And in diagonal polarizer, the other half of bits chosen randomly, not sequentially, any photon she will choose, but she will encode using a diagonal polarization basis. And then D plus 45 polarization 4. So D plus 44, so that is this one, black one, and the D minus 45, they are 3 here, so green. So how many green are there? 1, 2, so D minus 45, right? These are minus 45. So in diagonally minus 45, so 3 photons have been polarized like this. And how many she has polarized? Plus 45, 4. So this is plus. So 1 black, 2 black, 3 black, 4, correct. So 4, it has polarized in this direction. D plus 45. Now, how will she polarize? That might be a question troubling you. So let me answer it. Actually, it is Alice who will decide. Randomly, she will choose any of them, and as per her wish, randomly she will go for polarizing horizontal vertical as well as anti-diagonal diagonal. So generally, we call it as diagonal. I will also use the word D, HV for horizontal vertical. So, but when I'm saying D, doesn't mean that it is only diagonal, it is also anti-diagonal. So plus 45 and minus 45. So this is how she has polarized using the polarizer. Then they are traveling through, what is this? They are traveling through the channel, photon channel, right? So the receiver bob, what will it do? Now she has sent the photons, that means she has sent a series. Now what series she has sent? Let us see here. This is 1, okay? This is 0. You can see all horizontal are all horizontal are 0, vertical are 1, and right diagonal is 1. Where is my cursor? Yes, right diagonal is 1, and the anti-diagonal is 0. So let's see. 1, correct. Then this is 0. Again 1. Again, this is the problem. Again 1. Then again 1. Okay. Then 0, 0, 1, 1, 0, 0, 1, 1, 1, 0. So depending on whether they are diagonally polarized or horizontally polarized, it will take the decision. I mean, it will take the direction. And then what happens? It is passing through here, right? It will reach to the bob's end. It is reaching to the bob's end. When it reaches to the bob's end, there are 2 beam splitters. Where are they? Yeah. This is diagonal beam splitter, and this is the below that is the horizontal vertical beam splitter. And you know that, just remember, brown is for HV beam splitter and the black or dark blue is for diagonal beam splitter. Now, because two states are coming, so you will have to split them. Now, they will be splitted in 0 and 1. So, photon detector is there at Bob's end, and this detector will detect whether the 0 is coming or 1 happen, that the Bob is going to measure, and Bob will apply these beam splitters at his wish, not according to Alice. Alice might have used whichever polarization for sending the photon, but at this end, the Bob will measure this, will detect this using the photon detector, and the Bob has applied, which the first one is, for first it has applied, you can see in this picture, for the first it has applied the HV beam splitter, and the measurement was 1. That means what? That after beam splitter, the measurement is 1. Then it has applied the diagonal beam splitter, but this time after the superposition, when it got collapsed, then it has collapsed in 0. So like this, it will go on measuring, and this is the Bob's measurement. Okay. Now, Bob's detection is again at the wish of Bob. No one can force Bob to go for a particular beam splitter. It is the Bob who has to decide that out of 14 photons, which particular beam splitter it has to apply. So he has applied, and then after superposition, we never know how it is going to land, whether we will get 0 or we will get 1 after the measurement. So these are the measurement which Bob has got. So in this example, it has got these values. Okay. Now, how the shifted key will be created? For creating shifted key, the Alice they will talk with each other. They will communicate with each other, and Alice will give all the polarizers, that how she has polarized the bases, that whether it was HV base or the diagonal base. The first photon was polarized with this base, second was polarized with this base, and Bob will check the corresponding. So how he has splitted using diagonal beam splitter or horizontal beam splitter. So whichever will mismatch, they will be eradicated. They will be removed from the scene, and remaining will become, it will reduce the key, the actual key which Alice has sent will be reduced, and whatever left will be the shifted key. So let us try to understand this in another picture, but right now I would like to tell you, if you have understood this, then just look at this. This is HV, this is HV, this is HV, and the measurement is 1. HV1 measurement, the HV and the measurement is 1. That means this will be considered 1. Go to next. What is this? This is horizontal. Now in horizontal, 0 is okay, but this is being the beam splitter was the diagonal one. It will not be considered. Just write dash here. In third case, again it is diagonal. So diagonal plus 45. That's why it is 1. This is diagonal, but it is 0. So this is anti-diagonal. That means they are not compatible, and therefore dash. Now again in this is the same case as the first one. I will not discuss this, rather I would like to discuss this. Here, this is minus anti-diagonal. That is why it is 0. Again with splitter is also the splitter is also anti-diagonal, and it has measured value 0. So this will be 0. This will be counted. So this way all of them will be counted, and then they have discarded. You can see 1, 2, 3, 4, 5, 6 got discarded. That means you will get a key of 1100100100. They have represented HV with this both the up direction is the vertical one and down direction is the horizontal one. And same here, the forward direction is plus 45, backward is minus 45. So this is the representation of the vertical one. So vertical is always 1. This is the horizontal one. So that is 0. This is minus 45. So 0. This is plus 45. So it is bit value will be 1. And again, this is plus 45. So bit value will be 1. Now this is Alice ka basis. This was the Alice ka basis. And these are the states the photons are representing, and we have computed our bit values using these states of photon. So now your picture is clear that how we are trying to get the value 0 and 1 by measuring the state, by knowing the state of a photon, that how they have been polarized, in which particular state they are coming. So if they are polarized in horizontal or vertical or plus 45 or minus 45. Now in Bob's basis, what happens? I told you that Bob is free. It doesn't matter that, it doesn't, he's not bothered about what Alice has done. Irrespective of that, he will do it. So first HV, then plus minus 45, again diagonal, anti-diagonal, then HV and HV he has applied. So first he has applied, but the state he got at the time of measurement. At the time of measurement, he got this vertical. So vertical is 1. Horizontal he got, so plus 45 ka, this is plus 45 ka, so this is plus 45, so 1. This is minus 45, so 0. This is horizontal down, that means this is HV down, that means this is horizontal, value will be 0, and for this also 0. Right? So now bit values, you come, now try to find the shifted key, HV. This is tallying everywhere, so 1 will be retained. Okay, so how many of you have computed 1? Just see. And in second case, what happens? The HV and outright you reject this because they are totally different bases, so no need to compare. Then again, same bases, same bit values, fine. They will retain 0. Again here, different bases, eradicate. Again, different bases, eradicate. So what will be your shifted key? It will be 1 and 0. 1, 0 will be your shifted key. Now this is the actual diagram. I have designed this for you people because it could have been difficult to understand it here, and therefore actually this is the same picture. You can see Alice ka bit sequence. It is 1 0 1 1 1 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 1 0. So it is same. Okay. So this I have written here, and these are the states. And first is being polarized from here. I have taken first is polarized HV. Second, and second is polarized as, again second is polarized as HV, but because it is horizontal, that's why I have given blue color to it. And then D plus 45. So you can see D plus 45 is black in color, so I have given black color here. Fourth represents again HV. Fifth one is minus, right? This is minus. So this is being represented here, D minus 45. So this is actually the same picture, and Bob's detection. So these detections are copied over here, and then Bob has measured. So after measurement, we got this, and the shifted key. Okay. So that you have to compute and again check something here. Let me take a pen, and then just this they have given again. So they are similar. You can see because they are actually, the horizontal is little bit tilted, right? So they have made it very clear here. So just now you don't have to look here, but this is the picture very nicely given. This is your photon source. passing through your polarizers, getting polarized, and then they are traveling, reaching to Bob, and then Bob using beam splitters, and then the detectors are detecting them whether they are 0 or 1. Okay? So now here the basis which Alice said, this will be diagonal HV. DA बोलूंगी, okay? DA, HV, DA, HV, DA, HV, D. Okay? So now this is base sequence, okay, which Bob has used. Now Bob has used the HV, DA, HV, DA, HV, DA, HV, DA. And the photon detector said 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0. This is what we got. Now you have to compute shifted key. Are their bases same? No, no?
No.
No. So this one.
So dash.
Then bases are same,
Same.
value is also same.
Yeah.
So 1 will come here. This will be 1. What about this?
No.
Bases are not same. Yes. What about this?
Next is 0.
0. Because bases are same and the value is 0. So this will be considered.
Next also 0.
Next also. Will it be 0?
0.
Yes. Because bases are same. HV both and 0, 0. Then next
Will be 1.
will be
1.
Will it be 1?
Yes.
Yes, it will be 1. Next,
Discard.
discard because bases are different. Then
Discard.
discard. Why? Because again bases are different. First one is HV, another is diagonal. So discard. Then consider this, right? Both are diagonal.
Yes.
1. This
Discard.
discard because first is diagonal, another one is the Bob is trying with HV. So discard. Then this
1. Vertical.
1, correct. And
0.
this one again 0. So this is our shifted key. Okay. That is 1, 0, 0, 1, 1, 1, 0 will be your shifted key. Okay. So you can try it later on once again. Now one more example we'll go through so that this will be clear. But this, I've taken this because I liked it very much. Very nicely it has given that what Alice does is just a revision. Alice sends randomly polarized photons. And polarized photons are 0, 45, 90 or 135. We are calling it as minus 45. So if we go with x-axis, then we can say 0, 45, 90 and 135 to Bob. Then Bob, what Bob does? Bob randomly measures in the straight or diagonal base. So here they have written straight for our plus, that is HV. And then Bob keeps his result secret, doesn't disclose it, and Bob publicly tells his measurement basis, not the result. This is the result was 0, 1, 0, 1. So he publicly tells this, the basis only. Actually, this is the result, but because if you we are computing this into 0, 1 value, so actual result is this. But these are the bases. So this basis he will tell, the Alice publicly tells him that if he choose the right base, publicly means not through any other channel, just through telephone or through mail, they can communicate with each other openly. So what do they mean by publicly is that freely they do it, and then they tell you whichever are matching. So whichever the right bases they have used, and then they both of them keep the only results which have common bases and common states. And then they both have now a common and a random key. So you can compute the key for this also. That's why I have done it. And now let us try to implement it. Okay. Now for implementing one-time pad. So what for we are doing all these exercise, right? So it is not for fun, actually. It is a very much enjoyment when we succeed in getting the shifted key, that yeah, this was the key shared between the sender and the receiver, and this was made use for dealing with a secret, very confidential data. So we are master of that. So this is how it gets evaluated. So that we came to know, but how this will be implemented. So actually what they did, that one-time pad is a classical method. So in cryptography, the one-time pad, it is an unbreakable classical encryption technique, and this cannot be cracked theoretically, and it guarantees perfect secrecy. But the problem is that it requires the use of a single-use pre-shared key. So that key will be shared before going into the sharing mode, like when you are sending and receiving, you are sharing it. But prior to that, you need a key, and this key can be used only once. So and this should be larger than or the size of the equal. It should be either larger than or equal to the size of message which is being sent. Now, crypto systems, first it was proposed in 1882 to preserve confidentiality of telegraphic messages in old days, and it used a pre-shared key, that is, its size must be of the same of a Bogger or the message size. And in this scheme, every key is used only once. So that is why it is known as one-time pad. Because of that, its name is one-time pad. Then QKD helped to create these super secret keys which we need for one-time pad. So this is how, what is QKD is here doing? Quantum key distribution using BB84 protocol, we have learned that how quantum key can be achieved. So this QKD is helping to create this super secret key. So we have already created this super secret key, which we will need for our one-time pad to encrypt messages. So it is like having a super secret code that is extra safe. That is extra safe. Like using other methods, they required a random key that is at least as long as the message. Yes, this is one thing you have understood about one-time pad, that it requires a random key, and it encrypts by performing a bitwise XOR operation. So we will have to perform a bitwise XOR operation between the message, that is the plain text, and key. So then it will be encrypted, and for description also, we will have to use another bitwise XOR operation with the same key. And this is how we can access the message which is being transmitted. Now, this is, everyone is familiar, very much familiar. But now what we are going to do is, let us select a message. So I'm selecting you 8-bit message for simplicity, because for understanding purpose, we have to go with a small data. So now I'm selecting you as a message, and because it is very nice binary code 01010101. So let's go with this. Now, this message, it can be stored in L-bit register. So L-bit register has 8 bits, and it is encoded with the use of key that is named as KEY here, and which is also a number between 0 and 2 raised to power L minus 1, because 2 to the power L minus 1, it will be minus 1 because we are starting with 0. Now, the encoded message, MSG, is simply nothing but ORG plus key. The ORG is your original message, okay, and then the key will be added to it. The message, when it is XORed with K, the key, then what is this message XORed with key? Message is nothing but your original message XORed with key. And at the receiving end, for decoding also, you are adding another key here and XORing it. So these two gets cancelled and the original message is retrieved. So let's go through example. Let's suppose the message is 01010101 U, and before parting ways, suppose you are sending a message U to your friend and you have agreed on a key using a coin. So what should be the key? You are saying it will be 11111111. Your friend is saying it will be 00000000. Fighting, so don't fight. So you decide that we will go with a coin, head and tail. If head comes, we'll take 0. Second time, if tails comes, we'll take 1. Again, if head comes 3-4 times, then 3-4 times we'll take 0, 0. And so this way we will generate. Or you can choose any other method, classical method, for generating a key. And both will have made sure that they have the same key. But now here is a twist. In one time pad till now we were doing this. But now there is a twist that you are using QKD, both of you, for obtaining the key. Instead of using head and tail or any other classical method, you are using the BB84 protocol for generating that key. Okay? And then now the Bob has, the Alice has that key, and the Bob has also that key. That means now you and your friend. So you have one key and same key your friend is having, and you will be using same. So now, when first of all, the message which you are sending, that is original message, is this 01010101. And for ciphering, you will have to cipher this text. So you will XOR with this key. And now we have taken the key for simplicity. Let us suppose the key which we have generated using BB84 protocol QKD method is 11110000, and both of you have the same key. So now you are encrypting your message using this. And when you encrypt your message with this, that means now just compute them. And for computing, now you need this in bitwise operator, XOR operator. When the bits are similar, they result in 0. When they are dissimilar, they result in 1. So if it is 0 plus 0, it will be 0. 1 plus 1, it will be 0. But 0 plus 1 will become 1, and 1 plus 0 will be 1. So now just do this 0, 1, where it is original, and compute this. Yes. So similar means 0. These are dissimilar 1, similar 0, dissimilar 1, similar means 0, similar means again 0, dissimilar means 1, similar means 0, and dissimilar means 1. So this is your encrypted message. Now this message, it is being stored in MSG. Your original message is in ORG. Okay. So your original message is U, that is 01010101, and the encrypted message is MSG, which you got after using your key, and you have encrypted it using the XOR. Now you have sent this not to Bob, of course. Now I have asked you to share this with your friend. So you are sharing, you have sent this cipher text to your friend, and your friend's end, it will decode it to read the original message. And for decoding, again, because both of you are sharing the same key. So again, key, same key, that is 11110000. That will be shared. And then what will happen? Again, XOR. So message, XOR key, this was the formula. But now let us do it practically. So this is your message which you have received, your friend has received. And this is the key your friend is also having, and you are also having. He is using same key for decoding the message. And now see, similar 0, dissimilar 1, similar 0, dissimilar 1, similar 0, dissimilar 1, similar 0, dissimilar 1. So what is the message? Now decode it. 0, 1, 0, 1, 0, 1, 0, 1. So what will the message? Now let's go back to our eavesdropper. All exercise we are doing just to prevent us from this eavesdropper. Now here, how eavesdropper will get defeated. Because we are using quantum physics here, the main role of quantum physics will come here, and eavesdropper, it will save us from eavesdropper. So every time the quantum mechanics is coming for our help, till now it has helped us with superposition, using photons and transmitting bits using photons as photon particles, single photon particle. Using that, we have already created 0 and 1. So it is all because of quantum mechanics. And then superposition states. Again, the quantum mechanics came to our rescue. And now let us see that which principles will eavesdropper's name is Eve. So Eve tries to eavesdrop and to measure each of the Alice photons. So in between jumping and trying to measure the Alice photon before it reaches to the receiver Bob. But the moment she tries to confirm with the Alice that, like Bob has confirmed with Alice, right? So she will also have to confirm with Alice and she will get exposed. So she just can't do that. Photons, you know, once measured, they will get destroyed even before reaching to Bob. So the measurement has been tampered with. So it will be known to both. Both of them will come to know about that because photons are indivisible. Once it hits the detector, the photon no longer exists. So if Eve has hitted it while detecting it, so definitely she'll have to hit it. So while detecting it, it will not exist, and at Bob end and at Alice end also some message will give. And generally, mathematically, it is said that the Bob should receive 25% of transmitted photons. So Bob can be certain that the traffic is being snipped or something is being is wrong in the system. So he can very well guess and will alert. Now let us suppose that the malicious attacker named Eve tries to eavesdrop and to measure each of the Alice photons. Now, yes, this we have already discussed, right? The another thing is what saves us. In classical, you can see that the quantum keys, secret keys are being transmitted like this. In one-time pad also we have seen, that is why I took this letter. Because in one-time pad, it is very clear that both have the same key, and in classical public channel also, using those channels, they have shared their keys. And it is so very risky, even if you are sending it through mail or telephonic messages you are sending, or whatever media you are, they can be intercepted by anyone. But the quantum channel, it is safe because here you are using the photon channel, right? So that's the beauty of quantum mechanics. Here also one more diagram. In classical channel, bombardment, anyone can, so no security here, it is going through quantum channel. So quantum channel is much, much, much secured as compared to classical channel. So very nice picture I got, that it is bombarded, being anyone can interrupt and can get access of it, but in quantum channel it is very, very safe. And the reason being that why quantum cryptography is secure, that it relies on the fundamental laws of quantum mechanics. Now, Heisenberg's uncertainty principle says that any attempt to intercept or measure the photon during the transmission would disturb their state, and disturbances will be detected at both the points. So this is what is being achieved, which I have discussed earlier, So it is all due to Heisenberg uncertainty principle that if disturbed, then at the both points, the disturbance will get notified, alerting them to the presence of an eavesdropper. And then another is the no cloning theorem. Now, no cloning theorem says that creating an exact copy of unknown quantum state, because the quantum state is not known to Eve, and if Eve tries to copy it, then the copying process is, it just can't copy it. It is impossible. Therefore, the laws of physics, they guarantee the communication channel security, making it impossible to hack. Possible to not being hacked, but rather better word would be impossible for being hacked. Summarize. Heisenberg's uncertainty principle, no cloning method, no cloning theorem, and principles of photon polarization are the key players. Then measuring the quantum state of a particle is impossible without disturbing the system. Third point is light photons can be oriented or polarized in a specific direction. And because of that, we can produce a bits out of it. And these orientation can be used to represent the qubit in encompassing ones and zeros, because we do need ones and zeros, whether it is classical computing or quantum computing. The qubits are either in one of the two eigenstates of either rectilinear 0 to 90 or diagonal 45 or 135. And the eigenvalues which are assigned, corresponding eigenvalues are vertical is 1, horizontal is 0, positive plus 45 is 1, minus 45 is 0. Then Charles Bennett and Gilles Brazard, they developed the concept in 84, and these bits can be used as a reliable method for forming one-time pads and support system to deliver keys in a secured way. Then the key is transmitted from encoder to decoder by transmitting a large number of qubits. For simplicity, we have taken only 8 bits, but usually one will need at least 2L of these and one register of at least 8 bit. So total 16 bit. And if the decoder measures the spin in same direction as encoder prepared it, then it is a good bit. So we have counted good bits and we have taken them in shifted key. And if those measured in different directions, they are termed as bad bits. So we put dashes for them. To build the key, bad qubits are discarded and remaining good qubits are retained. So this now you know very well. The secret key is generated through quantum channel, and the intrinsic randomness of quantum states and their measurements provide the randomness in the creation of key. So we don't have to put values in a sequence of 1, 1, 1, 0, randomly you can. Then moreover, the QKD exploits the no cloning theorem, where quantum states cannot be cloned. So they cannot be copied, and therefore we have a unique key. Furthermore, the uncertainty principle that is presented by German physicist W.K. Heisenberg make the QKD process strong against the interception and retransmission attempts, because even if you just try to hit it, it will get collapsed. So nothing can happen. Neither it can be intercepted nor it can be retransmitted. So they cannot use any other technology that all these photons which are coming from Alice can be retransmitted, and then somehow with getting in connected with the Alice, they can retrieve the secret key. So this is not possible. And with Heisenberg's principle, the existence of an eavesdropper is revealed. That also we have discussed. The only task of quantum cryptography is to distribute the secret key. So please look at this. This is the most important point, that quantum cryptography will give you a secret key. It can be it will be distributed between the sender and the receiver. And this is what is quantum key distribution. Now, why there is a growing demand of quantum safe solutions? So, yeah, because the world anticipates the arrival of quantum computers and they are capable of breaking the traditional encryptions. Therefore, the demand of quantum safe solution is there, because once they are in the market and the quantum cryptography, the quantum cryptography takes its place and plays its wide role, then definitely the quantum safe solutions are needed. And the quantum cryptography, with its ability to provide secure communication channels using the principles of quantum mechanics, holds the immense potential for giving the various revolutionizing various aspects of our daily life. Because every time nowadays we have to go through use password, there is a need to keep our data communication data safe, as well as our financial transaction should be very much safe. We cannot tolerate any hacking or getting them lost. Our financial transaction should remain intact, and we should have very much faith on them. And therefore, there is a growing demand for quantum safe solutions. It is early stage of development and deployment, but there are real world applications where it has been explored and implemented. So let's see. Before discussing further, I would like to share one by thought experiment, because you have already gone through thought experiment. Now this is my thought experiment, that what I want is that team for India to have a quantum voting booth. So as and when the voter press the key, the voter's vote should get deposited, recorded in the database in central server through 100% secured communication network. Because of quantum computing, this is very much achievable in future. And the result should get declared the very next morning, because quantum computing, it works with tremendous speed as compared to classical computers. So it looks achievable, and then it offers the quantum cryptography will offer 100% security. So everything is secured. So why not? We should have this kind of voting mechanism in our country. So let's hope for the best. So my dream may come true someday. And the applications, I will go quickly, because this is something which we can even read from here and there. But because the time is approaching fast, so I would prefer going to the post. I would like to give you some touch of post quantum cryptography. So applications, it is being used in financial services. Of course, we have discussed it a lot. Data centers, data clouding, because we have to secure our data. Then Internet of Things, the IoT devices are being installed. They are taking popularity day by day, and their security is from the cyber attacks is must. And then the next is defense and national security. Of course, in defense, I would like to discuss, it can enhance governments and defense organizations' capability. See, secure transmission is needed. Many a times they have to send a secure code, although the code itself is a secured, but someone if can hack that code and can decode it, then it will be a disaster, total disaster. So such type of the quantum cryptography safe solution is needed for military communication. It is very much useful there, because then the integrity of this critical infrastructure can be maintained. Then healthcare, of course, there also our data is there. We don't want to get our private data exposed. And then the authentication and identity management, of course, there also we need the quantum cryptography will play a crucial role. But the challenges are, of course, there. And which are the challenges? See, but is it already in the hand of end users? It is still in early stage of development, not yet widely available to end users in its purest form. The technology is primarily being researched and tested by academic institutions, government organizations, and selected industry players for those who could afford its cost. However, there have been some limited deployment of quantum cryptography in certain niche applications. So in terms of consumer applications, quantum cryptography is not yet accessible to the average end user. The technology is still evolving and there are challenges to address. So now let us see which are the challenges to address. Technical complexity is there. It requires specialized infrastructure. These systems are currently expensive and not easily scalable. Second, quantum computing development. Researchers are actively working on post-quantum cryptography, which is focusing on developing encryption methods that can be withstand attacks on classical computers from quantum computers. So this is another problem which is arising because of the uprising of quantum computers, that even they will be capable to attack the classical computers, and therefore we will see how what researches and what actions are being taken to prevent from this. Then infrastructure and standards. Establishing infrastructure and standardized protocols for quantum cryptography is essential for its widespread adoption and to ensure the compatibility between different quantum cryptography systems. So their compatibility is again another problem, and integration with existing system, because existing system are classical systems, so it requires modification to the existing infrastructure protocols to accommodate the unique features of quantum cryptography. So if we want to integrate with existing system, the quantum cryptography, if we are trying to implement in one-time pad, definitely it is a merging of two. So for that you need some different infrastructure. So integrating will again be a problem, and education and awareness, this is of course needed, and we have taken one step forward in this direction. It is highly specialized field and there is a need for education and awareness among professional decision makers and end users. So that is what we are doing right now. At least we are getting acquainted with whatever researches have been done and how it happens, and just trying to grasp the methodology which has been used in quantum cryptography. Despite the fact that quantum key protocols are theoretically well structured and designed, the real implementation has imperfections. So defective optical fibers, then unwell constructed detectors, some other loopholes are also there. They are becoming cause of the attacks that are performed against the QKD schemes. So there are various challenges that appear and are a subject of research. But despite of these challenges, the future outlook for quantum cryptography is promising. Then, post-quantum cryptography. Now, this is a field, it is also called as PQC. I'm sorry, I'm taking a bit more time, but please allow me to take 10 more minutes so that I can make you aware of post-quantum cryptography. I'll not go in details, but just I want to make you aware of it. So this is a field that focuses on creating new ways to keep information safe, even from powerful future computers, which are called quantum computers. So PQC, post-quantum cryptography, it is referred as quantum proof, quantum safe, or quantum resistance. And why this is important? Because the quantum computers are super powerful computers. They can break the codes we are currently using to keep our data safe. For example, the common method RSA, encryption, it could be easily cracked by quantum computers using the algorithm which we have already, I think we have not made the algorithm of it, but it was explained, Shor's algorithm. So that it would make it easy for someone to access the private information, because Shor's algorithm will break in few seconds. The new type of security to prevent this from happening, scientists are developing a new type of cryptographic methods or ways to keep information secure that even quantum computers would not be able to break. So which are they? There are four famous. We'll quickly discuss one by one. Lattice-based cryptography. It is a type of cryptography which uses very complex mathematical problems to keep information safe, and these problems are based on the geometry of lattices. And lattices which are like grid of points in many dimensions, not just the usual 3D space which we are used to. It will be a grid kind of points in different dimensions. And the key features, of course, there definitely. The key features which we can discuss is the math problem. They are so hard that even the most advanced computer find them difficult to solve. And therefore, it makes it very secure against hacking. Efficiency, definitely. The method used in this are not just secure, but they can also run quickly on computers, making them practical for real world use. So there are applications. So applications we can skip because we are running time. But the next is the code-based cryptography. So code-based cryptography is a method for keeping the information safe that uses a type of code that is very hard to break. So this kind of cryptography relies on the challenges of decoding or figuring out a special type of code known as linear code, which is very difficult even for superpower quantum computers. So the security of code-based cryptography comes from how tough it is to decode these special codes. Even with advanced computers, cracking these codes is really hard, and which keeps our information protected. The key size, the one downside is that the keys you need to decode the message can be very, very large. So they will have to work. The researchers are working hard because this can make the system less convenient. So because it will require more storage space, and it will slow down the speed also. So because of these reasons, they are working on it. And then the third is hash-based cryptography. So in hash-based cryptography, it is a way of securing information of using something called as a hash function. A hash function takes any input like a message and turns into a fixed size strings of characters, which looks completely different from the original message. And then this method is often used to create digital signatures. So there it is very useful, hash-based. So it is like digital version of signing your name and to prove that you have sent a message. So it is very much useful. And the security aspect is the strength comes from the fact that it is really hard to find two different messages that produces the same hash. Like we say now, our handwriting, everyone's handwriting is totally different. So handwriting experts can detect, even if they look very similar to us, they can detect it. So something like that. Two different messages that produces the very same hash is very difficult. It will never happen. So because of this, so difficult, even for future quantum computers won't be able to do that. So it keeps the information secure. Our digital signature will be a unique one in itself. So this is what is hash-based. And the last one is multivariate polynomial cryptography. Imagine you have a really complicated math puzzle involving many variables, equations, and solving these puzzles can be extremely hard, especially if there are lots of them to solve all at once. This is what multivariate polynomial cryptography is all about. So these are math expressions with more than one variable. For example, it may be 3x2 plus 2xy plus y2, 3x cube plus 2xy minus y cube, y raised to 2 or 3x, 3 multiplied by 2 plus 2xy minus y2, something like that. This is a polynomial with two variables, x, y, and the x and y. So finite fields, of course, think of these as a special set of numbers where you can do math, but only within the certain limits. It's like having number systems with a fixed set of numbers to work with. So this is how it is working. Even though the puzzles are tough to solve, setting them up and checking answers can be done quickly and efficiently just because of quantum computers. So this is all about the post-quantum cryptography. Key features: quantum resistance. They are designed to resist attacks even from the quantum computers. And diverse approaches. They use a variety of mathematical problems, making it harder even for quantum computers to break all algorithms. So this is what is post-quantum cryptography. Compatibility. Some PQC algorithms are designed to be compatible with existing cryptographic infrastructure and standardization, such as NIST aims to ensure that the broad adoption and interoperability. So current status and challenges: research is going on. It is still an active research area. Performance, it can be a challenge for implementation. Transitioning from current cryptography system to PQC, it will require a very careful planning to ensure that security is maintained throughout the process. So if I want to summarize this, it is a critical area of research and development aimed to ensure that our cryptographic system remains secure in the face of emerging quantum computing technologies. Each of PQC algorithm has its unique strengths and challenges. Ongoing efforts are focused on refining these algorithms and preparing for their potential deployment. So with this, it is coming to an end, and we can switch over to question answer session.
Ma'am, we have few questions in the chat box.
Yes.
Question from the Shashikala. She want to know about Bob's measurement is just a prediction of states, but not mandatory to the detection states.
Yes, it is definitely. It is not mandatory. It is just prediction. He is free to randomly choose it, and he has to. If it is fixed, if it is not if it becomes mandatory, then everything will fail in security. So that's why it is random. He has to select it in a random way.
Okay, ma'am. We have one question from Rishabh. With advent of better quantum computers, there will be threat to cybersecurity. I have heard that with the development of better quantum computers, RSA encryption can be broken and safety can be compromised. So how that can be prevented in future?
Yes, so post-quantum cryptography is for that. And we have already discussed that even the Shor's algorithm with quantum computer can break RSA in just a few microseconds. So that's why the post-quantum cryptography is there. So some algorithms are being designed to tackle this problem, which will exist, and you're very right, this will exist. It is going to happen, but they have predicted it, and lots of researches are going on, and these 4 cryptographic post-PQC algorithms are being taking its place. They will save us from this particular threat.
Thank you, madam. Dear participants, if you have any questions, you can unmute yourself and ask the questions. I hope there are no raised hands coming up. So it was very informative, ma'am. Thank you so much. Now I request session chairperson, Dr. Ashish B. Sasankar, sir, to deliver the closing remarks. Over to you, sir.
Thank you, ma'am. Thank you very much. Dear all delegates present for today's session. As we draw our session to close, I want to take a moment to reflect on the session what we had today. The topic of cybersecurity in quantum age is not just timely, but crucial as we look towards the future of our digital world. Over the course of today's session, you have explored into an incredible potential of quantum computing, as well as the significant challenges it poses to the cybersecurity landscape. You have explored how quantum computing threatened to disrupt the very encryption standards that currently protect our data and the need of new quantum resistant algorithms that can be a safeguard our information in this new area. Our expert also discussed the innovative solutions being developed, such as quantum cryptography, which holds the promises of unbreakable security. These advancements remind us that while computer technology presents risks, it also offers the opportunity to build more secure and resilient digital infrastructure. Our expert provided us with a comprehensive understanding to the current state of quantum computing and cybersecurity. The discussion today have underscored the need of proactive measures, strategic plannings, and continued investment in research and development to ensure that we prepare for the quantum future. Madam, you had given a new insight for the researcher and academicians. Thank you, ma'am. As we leave here today, I urge to each of you to carry forward the insight and knowledge gained from this session. The quantum age is not a distant future. It is a rapidly approaching, and the time to act is now. I would like to extend my deepest gratitude to our esteemed speaker, Dr. Aba Kandelwar ma'am, convener Chitra ma'am also, panelists and participants for their invaluable contributions. Your expertise and insights have been instrumental in shaping today's session. Thank you. Thank you very much.
Thank you